Hi, I'm Bobby. I'm a postdoc at ETH. I'm presenting our work today on outlier features. So outlier features, they're a phenomenon that occurs during transformer training. And what happens is that certain neurons in the width of the activation matrix become much bigger in terms of their activations compared to others. And this is problematic and has become a sort of an area of quite intense study because they have downsides in terms of if people want to quantize their model for improved efficiency later down the line. It's really difficult if you have a large dynamic range between activations in order to reduce the precision. And so in our work, we're interested in sort of understanding why this phenomenon occurs. So is it an essential property of good training, or is it actually a byproduct of certain design choices that were made during, before you start training, that lead to this phenomenon? And if so, how could we prevent this from happening? So we focus on two sort of areas really, like in terms of the architecture and then the optimizer as well. And basically the key takeaway for us is that actually, yes, we can significantly reduce outlier features compared to standard practices. So on the architecture side, we sort of focus on the normalization layers that are sort of ever present in transformers. And we show that actually if you remove these normalization layers and we design a transformer block that is able to match the standard transformer block in terms of performance, but doesn't have the pre-normalization layer present. So if you remove the pre-normalization layer with our transformer block, actually it significantly reduces the emergence of outlier features during training. So that's the architecture side of things. Of course, it's also a training phenomenon, outlier features. So it's important to also consider the optimizer and the effects of the optimizer. And so the key takeaway for us is that actually the optimizer is super important. And actually, if you use outlier features are caused by large diagonal adaptive learning rates. So this gives you a variety of ways in which you can prevent outlier features by reducing the size or the adaptivity of the learning rate you use. But perhaps the most interesting thing we find is that actually using non-diagonal preconditioners, for example, soap or shampoo, are an effective way of both improving the convergence speed of your training, but also reducing the outlier features that emerge during training. And the reason for this is that these these non-diagonal methods apply a rotation to the parameter space before you optimize them. So yeah, that's sort of like the main sort of takeaways in terms of how our design choices that we have affect outlier features and their emergence. And to conclude, we sort of show that actually the suggestions that we propose to reduce the outlier features directly correspond to improved quantization performance, which we show in the final experiment here. So yeah, the takeaway would be that outlier features are a byproduct of the standard design choices that you make when you train a transformer, and there are alternatives out there that can reduce the outlier features and improve quantization performance, but also match or improve conversion speed as well.